I should be very careful what I say. It's not video recording, just audio recording, right? Wow. Well, then everyone is going to witness that I don't have my slides with me. I mean, the thing that I mentioned, that whether you should do a PhD or kind of go to industry and start working. I gave that talk at Harvard several years ago, but then it's lost in transition. I just started here, by the way. The ones who wouldn't know me, I'm a new professor here, and I just started last week. And I even don't have my computer with myself. And I'm going to talk a little bit about what I did before and show you some examples of, and also try to define what computer vision is and some examples, results of some of the projects that I did. I'm looking for PhD students. And computer vision is an amazing field to kind of work in. There are a lot of possibilities. It's a lot of fun also. Well, since I don't have those slides, I will kind of try to use my fingers, hands, and then please kind of also, this is, I assume, very informal talk. It's not like I'm going to present and then we have this questioning session. You can interrupt me anytime, actually. You can ask, so it would be more kind of casual talk in a way. I like you to get inspired and maybe kind of if you have any questions, just ask me. And that's the goal, right? I mean, if you kind of learn kind of anything from this talk, that would be to your advantage. So before I started here at ANU, thank you so much. You are very kind.
Microphone there.
Should I use it or?
For the recording.
For the recording? Okay.
Just check the switch on.
It is not this sturdy. I will just put it in there.
On.
All right. So at my previous position, we have been thinking about kind of like these big ideas that can change the world, and kind of everyone wanted to kind of come up with these disruptive, innovative things in science, not in just computer vision, not in just engineering. It could be anything, and that's what we do. That's what you would do if you are a PhD, if you have a PhD degree. So let's see what I have here in my slide that I put in like 10 minutes. Okay, this is personal background. Maybe before personal background, I can talk about the career paths. All right. So when you graduate, you will have two options. And by the way, no one told me that we have two options. I was just following the mass. I mean, like, I was looking at my friends and whatever they are kind of dating cool, I was just following them. And this is maybe 25 years ago. And I made many, many mistakes. I started at UC Berkeley, and at that time, I had no idea about what university ranking is anyway. And then I end up somewhere in New York because I thought it's a lot of fun. It's not about university. In the past, it got maybe 4 or 5 Nobel Prize winners. But then when I joined them as a student, PhD student, it was ranked 40. So ANU is definitely a very good university. That university was ranked lower than ANU. So we wanted to make, I graduated, I had no money, right, in my pocket, and I wanted to have this world travel, but then my family wanted me to kind of make something more sensible, and all my friends, kind of, they are smart guys, right? I mean, they didn't want to just kind of go drive around or kind of go to Cambodia or China. They wanted to go to school and kind of become important people. I thought, hey, if they become, I will become also. And then I applied PhD programs, and then I become a PhD. I think I did the right thing by following the wrong reasoning. That's what I realized afterwards. So my other option was I would have started at a bank I'm an electrical engineer. My undergraduate is electrical engineer. I did math. I did computer science. So I did many other things. I was very good at chemical engineering and biology, but then I decided to kind of do some computer science. So if I graduated, I would get a very good position at a bank, or as an engineer or as a software developer, and then I would maybe in 5 years' time I would become some manager at the bank or at that kind of company. So my salary, and these are the US numbers, I mean the typical salaries you would get in the United States now, maybe as an engineer I would get 55 to 75 depending on the place. And then after 5 years, it would have been reached maybe 90, 100. If I do my PhD, I hire PhD students now. I used to actually in my previous work. They start at above 100K. This is US dollars. So financially, starting as an engineer, kind of staying at the school doing your PhD, then starting as a PhD engineer or kind of researcher, whatever the position is, that does make little difference. The only thing, if you are at a company, you will have your group, maybe you will do a little more management, but hey, next day, a PhD may join into that company. Since he has PhD, you have experience. 5 years, we are talking about 5 years, right? This is a fresh PhD coming, and everyone thinks that, this guy doesn't know anything, any programming or any real world problems. He doesn't understand from the products or anything like that. So there is this sensation. But right after a couple of months, that guy catch up with you, and kind of he's a PhD, right? He's a doctor, and kind of he has this advantage. He has this golden key of PhD. PhD otherwise doesn't do a lot. That is actually a lot of torture for you. You have to someone tells you to go do something, invent something, which may not be possible, by the way, but then, hey, you have to do it because you have to publish papers to get your PhD degree. So that is a training that prepares you to take bigger challenges. It is not like you will become a master of something, because I can confess that all my PhD students needed more reading after they finish their PhD or postdoc and everything. So there is no end of learning. Even a kind of undergraduate student might know as much as a PhD student. But PhD students have, after the training, they have this advantage. They know how to take torture. They know how to work maybe long hours or weekends. So it kind of prepares you to life. And also you get PhD, you become a doctor, that is nice, that's not bad. So when you, after 5 years, a fresh PhD and kind of an engineer, a software engineer would make approximately the same money, maybe engineer a little bit more, with more responsibilities, but the next 5 year with PhD degree holder would definitely have this gap, open the gap, and financially, even at an industrial position as an engineer, and there are amazing PhD doctor software engineers, the PhD holders who are working as an engineer, and they are kind of highly valued. And wherever you go, you are a doctor. No one can take it away from you. So I really, even though I did, by following the wrong reasoning, I wanted to like my friends, competitive nature, I guess I have. But the right thing, I think, to do, give yourself some time. Don't rush to think that you need money, because you will make money anyway. And these are the best years of your life. Honestly, it is. And school is an amazing place. It's very relaxed and comfortable. You have you don't need to work from 8 to 6 or 10, or, this is 8 to 10 p.m. And if you work for a company, a startup, most likely you will work over weekends anyway. It's not just the weekdays. So think about PhD. You will learn more. You will stay in the school. You will get your degree. You will get prepared for the life ahead of you, and you will not rush, and you are not losing financially anything, to my understanding. And other thing is, more and more students are following their higher education, like postgraduate works and PhDs and postdocs. And when you go into market, you realize that there are these people and you are just an engineer, and it will make a difference. It will affect everything later on. And some websites you can find even kind of financial and other things like how it compares, which one is more advantageous. So basically, the slides that I lost was showing these things with nice examples and pictures and kind of more things that I cannot remember right now. So I don't have those slides. I hope kind of this will satisfy you as the title of my talk. So now I'm going to just kind of do my advertisement of the computer vision for you. So I'm a professor here, and also I'm leading this computer vision research group at NICTE, right around the corner. And I'm looking for PhD students. Did I mention it before? The reason I'm looking for PhD students, I'm very late. I just started, so international students, I cannot get them. And I know there are amazing domestic students here at Australia. And I think a good PhD student would get free PhD. All the tuitions and everything is paid, to my understanding. And I like to get at least a couple of those good PhD students and kind of maybe do amazing things before. So before this position, I worked a long time at MERL, which is Mitsubishi Electric Research Labs. Mitsubishi Electric Research Labs, but this is in Boston, Cambridge, actually, United States. And it's right across MIT. The reason they established the lab there to get people from MIT, those PhD students, and kind of get them and kind of grow them. And because American people don't go to Japan and kind of spend the rest of their life doing kind of research. So this is a place to gather all the brains in the world, not from US, also from India, from China, obviously. I had a couple of students from Australia also. They were coming and doing the research. And kind of I'm leading the group, and our goals are research excellence, which means you are very visible, everyone recognizes you. This is very good. If you become an engineer, people wouldn't recognize your name, but in academic circles, your name will stay and you will maybe become famous. That was not my intention, though, to start. You may become famous by doing the wrong thing, by the way. You may become, everyone will know you. That is what I do. Even though I do computer vision, I talk about computer vision. Computer vision is an outlet to core technologies, core areas. What are those areas? Maybe machine learning, optimization, and those type of things. Statistical data understanding and kind of probability, the things that you kind of take the coursework that you are taking, those are the areas. And machine learning might be an application of those things. You can apply it into many different things. First, these are some of the things that we developed in the past. It was obviously, there's a camera or there's image or video, and that is vision, right? Computer vision, how it started was, okay, there is this robot, and robot has kind of cameras in their eye sockets, right? That is kind of an Android. When I say Android, it is not the operating system. 20 years ago, Android was human-like robot. Now I think it is completely different. Google stole that meaning. So computer vision, how it started, you may think that, okay, there is this Android robot, and then it's going to understand the world. It is going to sense, perceive as a human through the camera. So the input is image, right? But computer vision is not just images. It is actually just data, any type of data you can access. You can do computer vision. Obviously, HDTV is one thing. It was old. HDTV has this problem. You have small image and you want to expand it, but then you have to imagine the details. It's called as super resolution or kind of denoising and other things. And the data is huge. You want to compress and kind of uncompress it. So how are we going to do it? Those type of things. So that's one of the things. That's how I started at this previous position. Then we developed these surveillance systems. This guy, it was a breakthrough device. You could have connected maybe 256 cameras, and it will do all type of intruder detection and other type of things. Now it's solved. The new version is room air conditioning device. So here maybe not, but Mitsubishi has those room air conditioning, and there is a camera in it, and it observes you. Why? It knows you are here and you are stationary, and it knows your body heat temperature also. It kind of adjusts the airflow around you so you will feel more comfortable. So that is kind of to me not the best of the application, but yeah, it makes money anyway. And there is this industrial thing. There is this. This is not a helmet. This is a camera actually, like this ball-like thing. It's a big camera, and then this is a helicopter. These helicopters fly around and kind of, if it locates a fire, then it automatically tells the ground station, oh, there's a fire on this address. And there is this face recognition thing. It is old. You see, these are all solved problems. And there is this medical system. God forbid, if you become a cancer patient, and if you don't want to get a lot, or if this is your last resort, there is a tumor, big, and it's near your heart, which you cannot operate, you cannot just cut, or in your liver. I mean, we don't realize, but when you breathe in and out, everything inside moves, jiggles, constantly. And I was thinking, nah, that is not right. And actually it is, like when you kind of do it, it moves, internal organs, abdominal organs moves 4 centimeters. Breathe in and out. And then we have this device, some other mechanical engineer designed this huge cyclotron. It is maybe 10 times of this room, and there are magnets as big as this whiteboard, and in the magnets there are these heavy carbon atoms moving at the speed of light, and then there's a nozzle. You let them go, it goes through your skin at a certain depth, it releases its energy. It doesn't burn, it just destroys the chromosomes. When it destroys the chromosomes, then those cells cannot regenerate any longer, right? And that is the cells that you want to kill. Those are the tumor cells. But this is so kind of accurate. It is like a laser knife. Doesn't cut through anything. But since you are moving in and out, if you don't adapt it, you will kill everything on the pathway. I mean, especially if it's near heart or liver. Liver, you cannot replace liver. Heart, obviously. And actually, some people are heartless, but kind of that's a different story. And there is these satellites. I mean, there's a lot of, these are expensive things, right? Each one costs like $250 million. I know because we sold two to Turkey, Mitsubishi sold, and actually I'm Turkish, by the way. And this car navigation. Car navigation is maybe one of the best computer vision examples because you put those cameras everywhere in the car, inside and outside, and then you get a lot of video and thing, and you want to detect everything to make it safer, and so you wouldn't pay attention to the road, you just sleep, and then it just goes to Sydney, right? That would be amazing. So, cameras can do a lot of things. I mean, this is not a kind of zoomed in image enough. This is only 100 microns. Actually, you can go kind of smaller scale than that. Obviously, nanotechnology enables that. And this is an ant. And this is just one channel of information that comes to you through a camera. And far, this is the moon surface. I think there are even much better resolution pictures. And you can see inside. This is what is in your kind of eye. And you see the blood vessels, and you can tell, there is some problem here, and kind of you diagnose. And you can see outside, actually. This is not a camera. This is a kind of, do you know what it is? Yeah. And it's a radar, actually. So a radar is, you can think it is a camera, but its working principles are different. It's not passive, it's active. It radiates its own signal, kind of wave, and then whatever reflected back signal is reconstructed. And this is actually maybe 10 years old. The technology right now is more precise. And this is the one that you would be scanned at an airport, but there are much better things. You can frozen the time, of course. I mean, that's what you can do with cameras. And you can see heat. You can see a lot of things. You can see 3D also, right? I mean, this is Kinect and kind of... Now everyone, if you have $100, you can just go buy. So, as I started, computer vision is kind of making, let's make these Android robots like a human. But more general, let's make these cameras smarter, more intelligent. So you can say that that is the intelligence behind the eyes. There are many problems, actual problems, that you want to solve because, okay, you are getting some... First of all, I mean, even you are not getting any image. You have to construct image. So computer vision means you have to do imaging. You may sit down and design these lenses and cameras and everything, electronics. You have to come up with different sensors, and this is where people are making a lot of money, right? And there is this fingerprint sensor now on iPhone. Do you know the most common camera all around the world? And every one of you has one. Can you name? I'm sure you have one. You use one. Not your cell phone, actually. Your mouse. This is a camera, actually. You know, there's this LED and then it sees. And you can maybe... Here's a startup idea. Go try to use your mouse as a fingerprint reader. You can do it. If you can do it, maybe that is a very cheap alternative to those other things, but it can be done. So here is the camera. So, I mean, the reason I'm mentioning that you can come with many different sensing modalities, not just kind of like the kind of obvious cameras, right? And then you have these geometry problems because everything is in 3D now, it's in 2D suddenly. You have to solve it, or different views, multiple images. You have to kind of understand where the camera is, like how you put them together. So you do alignment and registration. Then you want to kind of do some funny things, like you want to detect people or recognize faces and kind of classify what kind of data it is. You want to segment important things. You want to improve the resolution, remove the noise, because as you know, kind of if you take a picture under dark lighting condition, it's not going to look nice. So all of them are computer vision. But kind of some of the things like understanding is machine learning, optimization, and kind of other things also, other mathematical, deep mathematical things. It is, of course, not easy being smart because, I mean, humans are amazing. We can say that, I can tell that all of you are students, human objects. But a camera cannot. Actually, a camera in this scene would confuse, for instance, that watch as a face, those signs as maybe face, kind of anything, a pole as a human. Maybe it wouldn't even detect me as a human because half of my body is not visible. So these are what computers are struggling. Humans are amazing, brain works amazing. Of course, our learning mechanism is a whole different thing. The reason it's difficult to make a computer understand something, there is so much variety in appearances of objects. If everything is same, like, okay, you can define like a kind of like this cup, red and white, that's easy to detect. But people have different faces, right? And different poses, different postures, different expressions, different races, everything is different. So it is really difficult to make a computer to learn all of these large variance in their appearance. And also kind of other problems, like our eyes are very high resolution. God bless, on the center of the eye, we have 100 megapixel resolution. It's good, right? That's megapixel? Yeah, it's megapixel. Or maybe kind of close to gigapixel on the very center. So it's very high resolution. Towards the size, it's a different story, but it detects motion better than the center, as you may know. Cameras doesn't have. I mean, even the best cameras you have, it's not 100 megapixel, right? how much? Like maybe 12, 13 megapixels. And we also use a lot of other information. We know we are in a room, right? I expect there is a desk and computer and kind of some projector and people and other things. But machine doesn't know that. It doesn't have any context. You have to tell it the context to distinguish, hey, this is not a kind of mountain scene. This is a classroom or kind of seminar room. And this is actually the data you get. And this is one of the applications, border security. And there is a dog here, there is an officer here, and there are like these illegal immigrants here. And this is real. And the task defined with very, very low false alarm rate to go and detect these guys. And you cannot kind of give false alarm more than one time at a day. So, can you really say this is a dog? Can you? You cannot. Computer cannot. But computers are good in many other things. I mean, computer vision algorithms. You cannot identify anyone from their fingerprint. That would be very difficult. And computers do it flawlessly, right? They are very good. And they can search like billions of things very fast. We cannot. So, these are some of the drivers in general computer vision area. There is this modality, different modalities, like heat sensing and 3D or image or video. And there is also another driver is this cost of the things. Some of the things now are very cheap. For instance, Kinect. 3D become extremely cheap, so now even definitely games, but other applications have like 3D things. So that's a driver. I think expensive and cheap put somehow next to each other. These slides are very old. I'm trying to remember. And there are cameras everywhere. Like I mentioned, I even didn't put the mouse here, but I managed to put iPhone, I guess, here, and other type of cameras. They generate a lot of data, and someone has to go consume this data, right? Explain data, interpret data. And some of this data is video. It's not just an image. And so there is this kind of whole branch of understanding, analytics, from like these goals. And like these are the things that you will see at a computer vision conference where like thousands of people goes and there is a track under segmentation, and meaning people goes there and kind of tells how their segmentation algorithm is good. And there is a whole another kind of community working on compression of the data, and these are thousands of people. You see the size of the things 3D. There is kind of another big society, and kind of now there are like things are coming. There's a conference called as Fusion. The name of the conference is Fusion, and last year 1,200 people, PhDs and kind of researchers, students attended. So it's big. It's not kind of small. There are a lot of things, like I said here, computer vision is actually pattern recognition, signal processing, optimization, math, and everything under it, and it's fun. And why people are trying to do it is because there is a lot of money, for instance, defense, especially, well, I'm coming from United States, right? All the money coming from this kind of military-based institutions, and their goal is, okay, we're going to detect targets, and that's what we want to do, situational awareness, we will catch terrorists and those type of things. But that's not the only thing. There are also a lot of kind of iPhone cameras, other type of cameras. If you do nice noise filtering and compression and super resolution, you can kind of generate better quality images, and you can sell your kind of cell phone better, I guess. And there is surveillance systems that are everywhere, and you don't want a person to sit in front of like these 100 cameras, spend all his life just looking at those video feeds, right? I mean, nothing happens most of the time. If happens, it's once a week or once a month or year. Well, in Los Angeles, it might be once a hour. Anyway, that is not some nice job anyone wants to do, so you want the computer to do it and kind of open the doors. There's face recognition. You don't need to call everyone every time, the security officer, because my badge didn't work. And that's a real story. I wanted to enter the building and I couldn't because it wasn't activated. I wish there was a kind of face recognition algorithm. And of course, TV, they are interested in this thing a lot because now 8 megapixel is coming. The resolution is now 2 megapixel, right? HD TV. But 8 megapixel sets you can buy in Japan. But, I mean, where is the content? How are you going to show anything? So there's, of course, these drivers, kind of everything goes to the cars, and medical is huge. So if you do PhD in computer vision, you will find a job, definitely. I mean, you shouldn't worry about kind of where you're going to go. You can go anywhere in the world, and they are everywhere. And these are some hot things, like from Euclidean space to manifold, kind of more funny things, kind of sparse representation, compressive sensing. These are the keywords. By the way, old keywords. Now it's different. These are 3-4 years old keywords, clustering, and these are the problems. Every year people are publishing but not solved yet. So, which is good. You can just keep publishing forever. I mean, you can become famous and can make a career of doing kind of work on something that is not solved. So, I know I don't have any time left, but for instance, these are some of the applications. Like, we wanted to track tumors, right? And you don't want X-ray, more additional radiation all the time, X-ray video, I mean, are you treating the tumor or just causing the cancer? So you would use maybe ultrasound, and you wanted to kind of check the shape of ultrasound. And here is the tumor. Ultrasound is good, but then tumors are not visible, right? And that's an algorithm, automatic algorithm running for you. So you may design such algorithms, which is cool. And you may actually kind of design something and you cannot see the output. I can't also see it here, so maybe there's a problem. Here again, the goal to find the motion, like I mentioned, and kind of visualize and count. And there's a nice application of computer vision I just recently saw. Like the nurses are using, they look at your skin and find veins, so they know where to inject the needle. Isn't it nice? I remember when I was a kid, they were trying to find it because I didn't have enough blood and kind of it's not visible. And anyway, so here is another thing. You will maybe track. Does it come? Now it doesn't come program. So this is a counter. You are trying to gather some statistics and kind of you know how they move, and then if someone is running, you can identify. And is it gonna run? Media not found. You would kind of learn the road and kind of these are automatic algorithms doing funny things for you, nice things for you, like maybe kind of zooming in here and tracking, and you can put virtual counters on the road, and that's how you get tickets, right? There is these cameras on the road. It gets kind of 2 consecutive pictures and then kind of knows it is the same vehicle, same license plate. It knows license plate. It reads, understand it, and automatically, if the kind of displacement is too much, then writes you a ticket. I'm sorry about that, but they can detect left behind items nicely. And this is here, kind of, it knows, so this guy left this thing here. It doesn't know, it just kind of looks at or something stationary, kind of alternative solutions. Kind of, let's see what we have. And kind of if someone is illegally parked or kind of parked more than usual, kind of it can give you. You can even detect something moving like this, a small boat in this data. Isn't it cool? Why? Maybe. Do you know what it is? No? Any guess? It's a boat, and this is a thermal IR data, which it sees the heat. I was looking at why C is brighter, meaning hotter, warmer, right? I think that's the reflections of the sun reflecting towards those waves, and then sometimes you see it. Both is obviously kind of warm. I don't know why. You can kind of look at this data, and then it becomes math, right? You can try to cluster, and you can find this great motion. Kind of, we can distinguish it from the rest, and kind of, well, let's skip. These are the things that you will spend a lot of time generating graphs and kind of, but doing cool things. Like that is maybe how our brain works. Like the data is changing, right? kind of some data, some samples, and some other samples, and kind of this is a classifier. These are the faces, these are the non-faces. These are the people, these are the non-people. These are kind of smart people, these are kind of other people. These are, I don't know, kind of chemical students, these are kind of electrical engineers. And then suddenly electrical engineers becomes dominant and then can you put a boundary between them like this? Or kind of, do you want to adapt? Do you want this thing to turn around? Kind of how you would learn. Learning is just putting boundaries. That's what I learned. I mean, it's very funny. But there are other things also you can do. Let's say I give you these images and or any vectors actually. It doesn't need to be an image. You can go learn a kind of basis vector, then something like that. This face doesn't have what? Illumination, right? There is no light in here, and this is automatic. And here, oops, you see, I mean, automatically also, you can kind of take an image and kind of decompose into these two things nicely. Why you want to do it? Because you want to recognize this face, and if you have this shadowy, not shady, shadowy images, it's difficult. Algorithm doesn't understand. Algorithm is better understand this one. Kind of something like that. You want to kind of detect highways just looking at the image. You want to maybe kind of, let's see, something moving in this video. This is obviously some UAV flying around and kind of just... my time is almost up and I'm just kind of playing things for fun, you know? And these are really papers that kind of you may write in the future. You see kind of, okay, there's something going on here, detected automatically, and kind of then, like here, this thing is being tracked, small motorcycle, and algorithm decides, oh, what am I going to trust? Am I going to trust this feature, or this feature, this feature? These are something computer kind of computes, takes the image and interprets, converts the image into some mathematical notion and kind of try to then decide which model is better and then kind of find it in the next frame to say, okay, I'm tracking. Or maybe this is cool if I can play it. I hope I can play it. Where is the target here? So I make you look at the screen all the time, right? Can you see it? No, you cannot? Actually, it's not that difficult. And this algorithm actually finds it very accurately. You cannot see it still. And this is a almost real sequence. The ones on the planes, kind of this type of plane, and then there is a small target and it's moving. There is something moving. Let me tell you, it moves straight. You still don't see it? Where?
This diagonal.
Diagonal? Where does it start? Which part of? Yeah, okay, perfect. Wow. Amazing vision. Yeah, I mean, if for the ones who doesn't see the target, it is here, here, here. You see the target? This is moving straight, just moving straight. You know, you can write an algorithm, this is very simple to an algorithm. And you can detect this thing and you can solve a very supposedly changing problem. So these are fun. But then you need to generate this type of graphs so people will be impressed and can put in the there is a tank here. Again, going back to UAVs and kind of, you want to detect this thing, so like this algorithm fails terribly. It goes detect with, I don't know, maybe the ground, some dust or leaves. This thing works better. And that's what you want to do. You see, problems are really challenging here. They are not just kind of simple, take my picture and kind of Photoshop it. You can Photoshop it also. And this is something else. You get this image, you filter it, and it becomes suddenly nice, right? Actually, I had a friend who would take such a picture and remove all the pimples. And he has, he's at Merle, and he has this applet I can try to sell, you know. You can do those type of things. But this is difficult, you know, because kind of, how you do it is interesting. You learn what pimple look like, and kind of you segment, kind of then you replace it, you kind of fuse it. Those are the nice things. You can, for instance, here you want to find which is in focus, which is those leaves. And then you can see that all the other algorithms are failing terribly. My algorithm works very well. Kind of.
I'm afraid we're going to have to wrap up soon.
I know, yeah. I mean,
One or two questions.
but the format is you can ask questions anytime, right? And this is not a formal talk that I like to. And my goal actually inspire you and kind of show you some of the things that you can do in computer vision. Kind of, wow, I had a lot of slides. I can't imagine. It's open for questions, by the way. I'm just looking at my slides and trying to see kind of what you can do. Wow, you should definitely work on computer vision. Oh, like a salesperson, right? This is a real problem. This is cool. So this is 16 times resizing. If you just do simple resizing, it becomes like that. But if you, and this is computer generated. This is not the output, I mean the original image. This is what this thing becomes like this. Isn't it nice? So, I mean, then what is behind those algorithms is, to me, kind of quite interesting. And you can really do those type of things. This is the original image and this is the super resolved version of that thing. And maybe on my display it looks better. And these are comparisons. You can take this image, you can compress it like 200 times. What is missing in this image? Perfect, yeah. I mean, it looks like everything is same here, right? But there is still some variety, like it's not exactly the same. But you know it is a building, and that's what you need to know on your car navigation device. You don't want to see kind of, these windows are open or there's something here. It is a building, right? That's what you want to. These are two faces. Can you recognize? No, you cannot. I mean, it's really difficult. But this thing, this guy, this thing, this guy, and it works 99%. Talk is over, by the way. I'm just kind of, this is my breakout time, showing more things, what you can do.
I'm afraid we may have to wrap it up there, but if you guys would like to see the other fantastic examples of computer vision, I'm sure we'd be able to make these slides available to the CompCon website.
No, you should come to my office and talk to me.
If you're interested in computer vision research. Thank you very much for your talk.
Yeah, thank you. So actually, we can just stop recording.
We'd like to present you with this token of our appreciation for coming today.
Thank you.
Speak to us.
All right, yeah, that's great. We can share this one if you come to my office again. Okay, the talk is over. And if you want to go, just leave. That's fine? That would be fine?
We do have another talk.
Another talk. I'm sorry. So, you shouldn't go anywhere. Wow, many, many things. I wish I was quicker. Sorry.
Thank you very much.